So now let's move on to part C. So in part C, we need to find the standard deviation of x. So this is all the information that we've gained so far from part A and part B and from the question itself. So last time we found that the expected value of x squared is equal to this expression. And so that means that first we find the variance of x, which by definition is equal to the expected value of x squared minus the expected value of x and then squared, which we can just substitute in the results we had from last time. So 1 over 2 lambda squared, and the expected value of x is just equal to 0. So you see that the variance of x is equal to 1 over 2 times lambda squared. So that means the standard deviation, which is just the square root of the variance, is equal to the 1 over square root of 2 times lambda. So this is your answer. This is your standard deviation. Now the next thing it wants us to do is to graph the function, the absolute value square of the wave function, which is this expression over here. And if you check out this expression, you can see that if, let's say, this is the x-axis, and then this is the axis representing the wave function absolute value squared, you can see that this graph is going to look something like this. So it's going to curve up over here, and then it's going to curve back down over here. And you can see that the graph kind of looks funny at this point, and that is because of the absolute value sign. So you can see that this graph is continuous, but it's actually not differentiable at this point. The derivative does not exist at the point x is equal to 0. So this is what your graph is going to look like. And here we need to mark the points, the mean of x plus and the mean of x minus the standard deviation. So you would expect the mean of x, which is equal to 0, which is right at this very point. You would expect the mean of x plus the standard deviation to be somewhere around here. And then the mean of x minus standard deviation will be somewhere around here. And you can see that everything is symmetrical. So this region would be the region within 2 standard deviations. So this is how you mark the 2 points on your axis. And then now the question asks us to find the probability that the particle will be found outside of this range. So you can see that this shaded region over here is the spread. This is essentially where you'll be most likely, where you'll most likely find your particle. But then outside of this range, that means within these regions over here, now we want to find the probability of finding the particle within the red regions. So let's try to calculate that. So by definition, the probability is just equal to integrating throughout these red regions. And then because this whole graph is symmetrical, instead of integrating throughout 2 regions, I'm just going to integrate through this region from this point all the way to infinity and then multiply it by 2, because both of these sides are different. So I can just calculate this one side and then multiply it by 2. So these 2 parts are equivalent. So the probability is just equal to 2 times the point, the mean of x plus sigma, which is this point, and integrating all the way to infinity. And then the function we're going to integrate is the absolute value square of the wave function, which by definition is a probability density function. So this is the formula by which you find a probability. So now you go from, so we know that this is equal to 0, and then sigma, the standard deviation, is equal to 1 over the square root of 2 divided by lambda. So now our integral goes from 1 over the square root of 2 lambda to infinity, and then we're going to substitute in the expression for the wave function square. And then we can take away the absolute value sign in x because we are strictly within a positive region. So this term is positive and then all the way to positive infinity. So we're always in a positive region, so I can just take away the absolute value sign. And then dx. So integrating this is easy enough. I'm just going to put the 2 back inside. So integrating the e term, I divide this by negative 2 lambda. And then this will be evaluated from 1 over the square root of 2 lambda all the way to infinity. So thankfully these cancel out, so there's still a negative sign. So when you substitute in infinity, you get e to the power of negative infinity, which is 0, and then you minus the term where you substitute in this term for this into this expression. So you get minus, so don't forget the minus sign over here, minus e to the power of negative 2 lambda, and then x will be equal to 1 over the square root of 2 lambda. So obviously these cancel out, and then these cancel out. So in the end, the probability is equal to e to the power of negative 2 divided by the square root of 2, which is just e to the power of negative square root of 2. And then if you plug this into a calculator, you'll find that this is equal to 0.243116734. So this is your probability. So you can see that this is a, well, I wouldn't say this is a very small probability, but you can see that the most of the probability resides within this region. So the red region only accounts for around 0.24 of the total probability. The rest of the 0.76, the rest of the probability is within this region over here, within the spread of 2 standard deviations.